All right, so we're gonna go ahead and go over the exam two, the practice exam two that we have, right? So the first question, right, is just the typical question you get every time. You should be able to do this pretty quickly, right? So for A, right, this is the C alpha. For the first one, cysteine, the side chain is just boop, 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 boop. The tyrosine is boop, 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 et cetera, et cetera, et cetera. Y'all know how this works, right? So A, I'm going to go ahead and skip. B, calculating the PI of this polypeptide, right? So if you remember, if y'all were here yesterday, you remember that I have a method for calculating pH that is basically the way that everyone does it, if I'm honest. So we take a look at the pK values that we care about, right? So it's the N-terminus of cysteine, right? So 10.78. I'm going to go ahead and write out this polypeptide here. So it's cis, tyrosine, glutamine, or sorry, yeah, glutamate, isoleucine, arginine. So it's just a pentapeptide. That's nice. Okay. So N-terminus of cysteine is going to be 10.78. Our group of cysteine is going to be 8.33. Tyrosine's R group is going to be 10.07. Glutamate is going to be 4.25. And then isoleucine is not going to matter. And then arginine, its R group is going to be 12.48. And the C terminus for arginine is going to be 2.17, right? So we list them least to greatest: 2.17, 4.25, 8.33, yeah, 10.07, 10.78, and then 12.48. Draw lines down under each of them. All right, charge of the most protonated part of this polypeptide, that's going to be +1 for the arginine, +2 for the ammonia, so that's going to be +2. Alternatively, you could do -1 for cysteine, -2 for tyrosine, -3 for glutamine, and then -4 for the C terminus. And then just follow that out. -2, -3, -4. All right, and then the PI is just the average of these two. So 4.25 plus 8.33 over 2, that is 6.29. All right, so that is for B. And then C, net charge of the polypeptide at these certain pHs. We have pH 1, 4.25, 10, and 14. And then charge pH. I'm just gonna make it a chart. Can y'all see all right? Probably. So at pH 1, that's going to be +2. At pH 4.25, that's going to be halfway between 1 and 0 because it's on the PI. So it's +0.5, and then or +1/2. That's probably a better way to write it. And then at 10, that's going to be I'm going to say he wants -1, but that would also be kind of a mixture between -1 and -2. But simplicity's sake, we're going to say -1. And then 14.0, that's going to be -4. Right? See there? Pretty simple. Okay, so D, you do a peptide buffer, or you put this peptide in buffer solution, then you use cation exchange or anion exchange. So we're just going to keep that chart here, right? So remember, if your protein is positive, you use cation, -1.5. Okay, so it is -1.5. Did he give us a weird chart, or am I crazy? And it's probably so close that it is probably -1.5. All right, okay. So I can understand that. So remember, if your protein is positive, use cation exchange, negative, use anion exchange. Don't think about it anymore, right? This is cation. This is cation. This is anion. And this is anion. Boom. Negative, negative, anion, anion, positive, positive, cation, cation. All right. So now we have number 2 here. Number 2 is we have this solution that has an absorbance of 1.018, a wavelength of 399, but I thought that's going to matter, a path length of 0.1 centimeters, and then molar absorptivity or epsilon of 62.0 inverse centimeters inverse molars. We need the concentration. We need to find the concentration in moles per liter, so molarity. All right, so absorbance is epsilon that, right? So concentration is just absorbance over epsilon length. Plug and chug, 1.018 divided by 0.1, then divided by 6220. All right, I got concentration is equal to 1 times 10, or sorry, 1.64 times 10 to the power of -3. All right. So taking a look at the answer key, that is correct. All right, cool. So 3, right? So 3 gives us these different proteins, and they're all in a gel. They're all in an electrophoresis gel. And they've given us a sort of thing, right? So we have to identify each protein based on how far it moves. Well, the smallest proteins move the most. The largest proteins move the least, and so we get so E has moved the least, right? And so E has moved the least, so E is going to be the biggest, which is 200 kilodaltons. Also remember that a dalton is just equal to a gram per mole. So kilodalton is just 10 to the 3rd grams per mole. Don't let that trip you up. I don't think we've had a class that we've seen that on, but you know. So D, C, B, and A. D is going to be 100 because it's moved the second most. C is going to be the next lowest, which is 50. B is going to be the next lowest, which is 25. And A is going to be the least, which is 50. So simple, remember that size and is inversely proportional to distance. in gel electrophoresis, right? So, and then B asks us to draw a graph with the log 10 of the molecular weight, right? So we need to take the log 10 of each of the molecular weights. So times 10 to the third. And then we take the log of each of these. So we take the log of that and we get 5.3. We take the log of the 100. Log of 100 is 2. Plus 3 is 5. Log of 50 is 1.69 plus 3 is 4.6, 4.7. And then log of 25 is 1.39 plus 3 is 4.4. And then log of 15 is 1.17 plus 3 is 4.2. All right, so this is the log of the molecular weight. So, and then we have to write down the distance that they've gone, right? So E has gone, I'm gonna go over here real quick. 5.3, 5, 4.7, 4.4, 4.2. And this is E, D, C, B, A. And then this is going to be the distance they move, right? So E has moved one distance, D has moved 1, 2, 3, 4, 5. C has moved 10, 11, 12. Yeah, 12. B has moved 5, 10, 15, 20, 25.1. I'm going to say 25 just to make it easy. And then A has moved 5, 10, 15, 20, 25, 30, 35, 36, 37. All right. So whenever you're drawing these graphs, you always want to be fast about it. Right, so don't worry too much about making everything look all pretty. Just kind of be like, okay, this is 5, 10, 15, 20, 25, 30, 35, 40, boom, you're done. And then here we start at, so label 5, 10, 15, 20, 25, 30, 35, 40. You need to label your axes. So this is distance. And then we have a scale of 5.3 to 4.2 on this axis. So let's say this is 4, 4.1, 4.2, 4.4, 4.6, 4.8, 4 or 5, and extend it a little bit, 5.2, 5.4. You could use the graph from the old exam. Yes, probably you can. Honestly, that's a good idea. If you don't want to draw out your own graph. I find that labeling the graph takes a while, but yeah. And my axes aren't correct. It shouldn't matter which one's the x-axis and which one's the y-axis. If you're just drawing unless it tells you specifically for each standard. Okay, maybe. I'm gonna say no. I'm gonna say he's an asshole if he does that. Normally, the answer key, I believe, has a log of molecular weight on the y-axis. I just didn't do that because I didn't do it. So then we plot our 4.2 at 37-ish, right? And what I'm going to go ahead and do is like label the points. And then 4.4 is at 25, so and then 4.7 and 12. All right, and then 5 and 5. That's kind of funny. And then what, 5.3 and 1. Okay, and then it wants us to draw a line of best fit through the points. So I'm just gonna kind of do this. I mean, that's not great, but use a pencil. That's what I'm gonna tell you. Use a pencil. Ignore the line I made before. Just, kind of draw that. There we go. That's a good way to do it. All right. He can't really count you off too much for them. Okay, so calculate the approximate molecular weight of band 1. So they want us to figure out band 1. Band 1 is at a distance of 1, 2, 3, 4. 1, 2, 3, 4, 5, 5, 10, 15, 20, 21, 22, or 21 and a half. So distance of 21 and a half would be like right here, going over to that point and going down. We get about, I'm gonna say, for C, I'm gonna say like 10 to the 4.52. I remember somebody, I forget who, asked Dr. Latham, right? Because if you're very slightly off, right, this is going to turn very different. Like the difference between 10 to the 4.52 is a lot different than the difference between 10 to the 4.59 than you would think in just like a 0.07 difference. And so they asked Dr. Latham if he was like going to be really harsh about it. He's going to give you leniency. Just always write out the 10 to the whatever, right? So that they know what value you chose here, because I bet you a nickel he's probably going to grade this value. So don't make it difficult on him. All right, and then 10 to the power of 4.52. 10 to the power of 4.52 is going to be about 33,113.1. I'm just going to do 3313 grams per mole. There you go. And then D wants to do the same thing, but with band 3. So look back up at band 3. Band 3 is about 6.5. So 6.5 would be like somewhere right here. We take a look at it, right? We go all the way along to wherever our line of best fit is. Go all the way down at that point, and we see it's just slightly over 5 I'm gonna say that's like 5.05. So D would be 10 to the power of 5.05. Be 5.05. There we go. I got a very ridiculous answer there. So that is 112.201 or O2. You round grams per mole, and then we leave it at that. So that covers problem 3. So then we have problem 4. All right, so problem 4 is, it gives us this gel electrophoresis thingy and asks us some questions about it. So we have, what is the name of the 2 dimensions in the gel electrophoresis experiment, right? So there's an x-axis and a y-axis, right? So y-axis being like up and down, x-axis being left and right, right? The gel looks something like this, and then you do that, and you got like dots here, and you've got like lines here. So the x-axis is going to pH, or sorry, PI. PI of the protein, right? Whereas the y-axis is going to be the size of the protein. So smaller sizes as you go down, larger sizes as you go up. And then with pH, normally there'll be like pH 4 here and then pH 10 here, right? So you can discern that for yourself. So what are the names? What physical properties do these separate the protein samples? I think that answer covers both of them. And yeah, that answer covers both of them. Or, well, and then the second answer here, pH and size. Yeah, size. Okay, so that's A there for you. Work in B, write the order at which the number of proteins would elute off a size exclusion column. All right, so size exclusion. He says x-axis is isoelectric focusing and y-axis is SDS page for dimension names. That is weird, but I actually have the thing pulled up. Let me look and see if that. That is weird. I guess, yeah. Okay, so x-axis is the isoelectric focusing. I guess because that, and then the y-axis is the SDS page. I'm guessing that is because that is the name of the thing you're doing here, because you're combining 2 different types of gels into this so that you can characterize proteins a little better, right? So you have this gel down here, which is the SDS page, and you have this gel up here, which is the isoelectric focus gel. So yeah, I'm gonna say you're right about that. So anyway, size exclusion, right? So the largest proteins in size exclusion, size is proportional. So size is inversely proportional to elution volume. Meaning that big first, small last, right? And so our biggest proteins in this SDS page are going to be the ones that didn't move very much. So they're going to be the ones closest to the top. So if we take a look at the thing here, right, they're ordered from the bottom to the top numbered. So like the bottom one is numbered 1, the top one's numbered 8. It goes up from there, right? So the order at which they loot off on a size exclusion column is going to be the biggest at 8, second biggest at 7, third biggest at 6, fourth biggest at 5, next at 4, third, 3, 2, and 1. And these are names of proteins on the little picture they give you on the exam for those who don't have it open. Excuse me. All right, you decide to purify the protein sample. C, you decide to purify the protein sample based on using an anion exchange column, using a buffer at pH 5. Write the order that your proteins will come off in. All right, so you're at pH 5, meaning that you're very, very, very acidic. Basically to the point where all of your proteins are quote unquote, all of your proteins really and truly should be like, they all should be positive. And so if we take a look at our thing, right? So with charge exclusion, all right, so what is it called? So ion exchange, that's what it is. The most unfavorable charge, so whatever's opposite of the, so if it's a cation exchange column, the most negative is going to be first. If it's an anion exchange column like we have, it's going to be the most positive stuff that's going to come off first. All right, so the most positive stuff is going to be the stuff that is likely going to be the stuff with the highest pI. Because that stuff at low pH is going to be really, really, really positive. But at high pH, it's going to be, it's neutral really, really high up. The buffer pH does matter. Because if it was, you were purifying the sample in an ion exchange column, we had a pH, not pH 11, right? All of these proteins are, their pI is below pH 11. And so they'd all stick to the anion column. But here we have a pH of 5, right? And if you look on the thingy, there's not a whole lot. Excuse me. Sorry. So you should get a protein that is, so you should, so anion exchange column, we get rid of the most positive stuff first, right? And so that's going to be the stuff with the highest pI, right? And so what it's going to be is it's going to be from the stuff with the highest pI to the lowest pI is how it's going to elute off. So we have 5 has the highest pI, and then 4 has the next highest, 2 has the next highest, 6 has the next highest, 3, 7, 8, 1. Fairly sure that is the order. Yeah, 5, 4, 2, 6, 3, 7, 8, 1. Okay. That honestly would make a lot more sense if I had bothered to print out the thing, but I didn't realize I didn't have COVID until today. Until like a couple hours ago. So yeah, my results came back negative. All right, 5. 5 is fun. I have had, okay, so 5, right? You have an alpha helix that has 78 amino acids. And they're asking you what is the length of it. So like it's a coil, right? What's the length of this coil? So if you remember that one of the numbers that you need to have memorized is that there are 3.6 residues, meaning amino acids, per turn in an alpha helice, right? So 78 divided by 3.6, that should give us 78, 3.6. That should give us about 21.6, 3.7 amino acids. All right, and then it wants the length of it, right? And so, or sorry, we're going to keep this as we're going to keep this in our calculator and not round because it wants the length. So we're going to go with the 1.5 angstroms per residue of a of an amino acid in an alpha helix. This is only true for in an alpha helix. So then we multiply by 1.5, and that gives us a length. Hang on, my bad. Sorry. This is not the right answer, not right thing to use. Sorry, I was going in the wrong direction. Okay, so they want to know the length of the alpha helix. So we take the 78 amino acids, and then we over 1, then we multiply by the 1.5 angstroms per 1 amino acid, and that gives us a total of 117 angstroms for this alpha helice. And then we take the, how long would the polypeptide chain be if it was fully extended? All right, so the polypeptide chain is 78 amino acids. Another number you need to learn is another value you need to know is that it is 3.5 angstroms per amino acid when not an alpha helix. So not an alpha helix is 3.5 angstroms per amino acid. When it is an alpha helix, 1.5 angstroms per alpha per amino acid. So we take our 78 amino acids, right, over 1, multiply by 3.5 angstroms per amino acid. I bet y'all can't see that very well, so I'm going to switch to this. And that gives us 78 times 3.5, 273 angstroms. And then, all right, so then we have our last problem 6. We cannot do B for 6 yet. We have not covered the Hill coefficient. He will not have that on the test. You're good. If you looked at that and you were like, I don't know what I'm doing. I'm probably really stupid. Don't worry. You don't need to know about the Hill coefficient, but you do need to know about how to do 6A. So 6A, right? We have a KD of 3 torr. And how much O2 would you need for, so we need to know the pressure of O2. This is how I'm writing pressure, right? This is PO2. It's not like the negative log of O2. That's pressure of O2. We need to know that pressure of O2. And we have a Y O2 of, so a fraction bound of O2 of 90%. All right, so we have this formula here. Y, the fraction bound, is equal to the amount of O2, the concentration of O2 over the concentration of O2 plus the dissociation constant, right? So that we can rearrange this to y O2 plus y KD is equal to O2, and then we subtract that, and we get y KD is equal to 1 minus y O2, and then we have O2 is equal to y KD. Oh, sorry. The thing is really small for me right now, so I can't quite tell whenever I'm in frame or not. I really need to like figure out what the frame is and just like put tape down here. That'd be a good idea. 1 minus y. All right, so this would be our formula that we use, right? We know what y is, we know what KD is, so we plug and chug. All right, so our, and we convert this percentage to the decimal, which is 0.9. So we have 0.9 times the KD, which is 3, divided by 0.1. And that gives us, we need 27 torrs of O2 to have a 90% bound. 27 torr O2 partial pressure. And the question also asks how much O2 we need for it to be 10% bound. So in that case, let me get another piece of paper. Oh, wait, do I need to? Okay. So in that case, we have the same KD. We have a different Y. So we have the same KD, which is 3 torr. Different Y, which is 0.1. But the same formula can be used. So pressure of O2 is equal to Y times the KD times the fraction not bound, or divided by the fraction not bound. Okay, and so plugging and chugging again, we get 0.1 times 3 divided by 0.9. So we would need an O2 concentration of O. So our oxygen concentration would need to be equal to 0.33 torr for us to have a 10% bound oxygen to myoglobin. And then they ask us, what's the ratio of the substrate concentrations at 90% bound over 10% bound, right? So ratio of the substrate concentrations at 90% over 10% bound. Okay, so 90%, right? We have at 90% we have 27 torr of oxygen. At 10%, right? So it's 90% over 10%. That is 27 torr over 0.33 torr, which comes out to 27 divided by 0.33, comes out to about 81.8. I don't know why he asked you for that. I imagine it probably has some use later on, but we haven't gotten there yet. So, but that is the full test. So that took us about, honestly, about 30 minutes if we cut out like some of the BS. And that was with explaining, right? If I was just doing that on my own, I wouldn't have written out nearly that amount excuse me, that amount of stuff. So yeah, our test is going to be longer than that. He's going to have more stuff. Yeah, I can go over how to get the 27 tour again. Okay, so we solve for this because that paper is messy. I understand. So we had this formula here, 1 minus y. So we had y is equal to 0.9. We had the KD of 3 torr, right? So we have this formula, these numbers, right? Plug and chug. We have our PO2 is equal to 0.9 times 3 torr over 1 minus 0.9. Right. Plug and chug that. We get so this comes out to 2.7, and then this comes out to 0.1, which just becomes 27 over 1 torr. So yeah.
Wait, so how did you get the 0.33 in the next part?
How did I get the 0.33 in the next part? Okay, so in the next part, I have a fraction bound that is 10%. So y is equal to 0.1 because 10% to a decimal is 0.1. Our KD is still 3 torr, right? So we have a PO2 of PO2 is equal to the fraction of, following this equation up here that we derived earlier, is 0.1 times 3 torr over 1 minus 0.1.
Okay, so you just replaced the 0.9 with the 0.1 for the 10% now?
Yep.
Okay, cool, thanks.
Whenever you're switching from 90% to 10%, and they give you the KD, and you're supposed to find the O2 concentration. Okay. And with that, yeah, I don't know how. And are there any other specific questions y'all have in mind?
I was gonna say on all the days that he used like the PyMol like program, like when he was showing us the structures of like primary, tertiary, secondary structures, do you think we'll have to know like anything specific from those days? Because I kind of got lost.
Absolutely nothing. I would bet you nickel that you need to know absolutely nothing. I bet you he did not plan to use PyMol those days. He just had.
Yeah, I kind of got confused like on the when he pulled up the program.
What did you go over the PI question? Yes, we did. That is all messy right now. That there. This was the chart that we used in the PI question. So this had pretty much everything there. And then D was right here. And then I kind of just didn't bother to do A because drawing out amino acid isn't going to help y'all. But I am going to go ahead and put an OH there. I mean, if y'all want, I can give y'all a really stupid problem that I think if he's smart, he'll make you do. If y'all are down for it. This was actually something that yesterday we ended up, I ended up coming up with the idea of it and then kind of lost my train of thought afterwards. All right, so in this problem, right? So myoglobin that has an oxygen bound to it. So there's a wavelength, right? Let's say the wavelength is like 233 or 242 nanometers. All right, that wavelength, myoglobin that is bound to oxygen has doesn't absorb, no absorb, right? But myoglobin that is not bound to oxygen does absorb. All right. I take a vial that has no oxygen in it, and I get an absorbance initial of, let's say, 1.108. I take my vial, I open it, and I add an unknown amount of oxygen in it, unknown partial pressure of oxygen. All right. I then take the absorbance of that afterwards, and it is 0.738. So it is Beer's law. All right, so I have that absorbance, right? My KD of this is 3 torr. All right, that's my KD. Excuse me. I'm so sorry. All right, tell me the partial pressure of oxygen that I added. Go. You have, I'm going to give you all 5 minutes. Starting now. Oh, and I use the same setup for taking the absorbance of both of them. Same cuvette and same instrument. All right. Were you able to find an answer in that time? Anyone at all who wasn't here yesterday? Because yesterday we actually went over this problem. All right, so here is how we do it. Okay, so we know that you guys will grant me that the absorbance initial, that's going to be equal to some constant epsilon, right? Constant for the material, times the concentration initial of unbound myoglobin times some cuvette path length. All right. Then the absorbance final is also going to be equal to the same constant epsilon because it's the same material and the same apparatus times the concentration final of unbound myoglobin times the same path length because it's the same cuvette. All right. So now if I divide, so in the absorbance initial is going to contain all of the myoglobin, right? All of the myoglobin and or bound and unbound myoglobin, right? So it's going to contain, so yeah, that concentration there is going to contain everything that is bound and unbound in the final thing. That is not what I got. So you'll agree with me that if I take the absorbance final, you are correct, Charlie. Charlie. If I take the absorbance final over the absorbance initial, if I divide the two, right, that's going to be the same thing as taking epsilon times the initial, or times the final concentration times the path length over epsilon concentration initial path length. These two cancel out, right? Path length on top, path length on bottom cancel out, epsilon on top, epsilon on bottom, those cancel out. All right. So the absorbance is the same. So the ratio of the absorbance is the same as the ratio of the concentrations. And same volume, right? So you'll agree with me that this is the same thing as the percent not bound, right? Because this is the myoglobin that wasn't bound after addition of oxygen. This was the myoglobin that existed originally. And the percent not bound, 1 minus this number, should give us our Y. Okay, so, this number here is 1 minus Y, which is our percent bound. All right, so we can then calculate our percent bound from that. All right, so the absorbance final over absorbance initial is going to be 0.78 divided by 1.108. It's going to be about, so absorbance final over absorbance initial is going to be equal to about 0.666. That's what we're going to go ahead and say it is, because I'm demonic. All right. 1 minus that is going to 1 minus 0.666 then is going to be equal to our Y. which that means our y is equal to 0.334. Okay. Our pressure of O2 is equal to y times the kd over 1 minus y. We have y. We were given kd. We've calculated y now, so we can find our pressure of O2. And so plug and chug basically. And that ends up being about 1.5 torr. So yeah, that combines, like Beer-Lambert's Beer-Lambert with this. I don't know if he's going to be mean enough to give us a problem like that, but he might. He might be running out of ideas for what to ask. All right. Let's go ahead and you want to do one more PI problem just because we know that that's going to be a question? I think that'll be a good idea. I'm seeing a yes, so let's go for it. All right, so let's redo the first problem, but with a different polypeptide. So let's think of like what's a good polypeptide? I like glycine. Glycine's pretty cool. Arginine, that's pretty cool. Histidine is my friend. Lysine is okay. And then what should be the C terminus? Have fun. Let's make the C terminus like tryptophan, my boy. All right. So calculating the PI, right? So if we wanted to go to, we'll start with B because A is just writing out the structure. B, right? Glycine, the C terminus of glycine is, N terminus of glycine is at 9.60. The arginine side chain is going to be 12.48. The histidine side chain is going to be 6.0. The lysine side chain is going to be 10.53. And the tryptophan side chain is going to be 10.07. Or no, tryptophan doesn't have a side chain, but it does have a C terminus, which means that C terminus is 2.38. All right, so list them least to greatest, 2.38, 6.0, 9.60, and then 10.53, and 12.48. All right, draw a line, draw a line, draw a line, draw a line. Okay, pH 0 is down here, pH 14 is up here. All right, so we have to find the most deprotonated or the most protonated form, whichever one's easier. With this one, I see that we have 3 basic ones, but we don't have any acidic amino acids. So I'm going to go with the least protonated form. So the negative charges that we'll see will just be from the C terminus. So at pH pH 14, that's going to be -1. And then we just fill it out from there. So we do +1, +2, +3, +4. All right, that makes sense. Okay, and then we take the average of these two pHs. So we have 10.53 plus 12.48. Divide that by 2, and we get the PI is 11.505. So really, really high PI. Really, really high PI, but we have 3 basic amino acids, so no shit. All right, C asked us what was the net charge of the polypeptide on these different pHs, right? So the pH charge All right, so the pHs it asked for 1.0, 4.25, 10.0, and 14. All right, so charge at 1.0 is going to be +4. Charge at 4.25, 4.25 is between these two, so it's going to be 3, +3. Charge at 10.0 is going to be between these two and sufficiently far from this that I can reasonably say +1. And then 14 there. At 14, we should have a -1 charge. All right. And then D asked us what ion exchange column would we use to purify this protein at different temperature or at different pHs. At these different pHs, what ion exchange we use? Cation or anion? Well, use the cation exchange columns to purify the cationic proteins, and we use the anion exchange columns to purify the anion proteins. So 1.0 charges +4, that's going to be a cation exchange. 4.25, that's going to be a cation exchange column because it's +3. 10.0, it's still a positive charge, so it's going to be a cation exchange. And then -1, pH 14 charges -1, so that's going to be an anion exchange. Yeah. So these questions, this is the one question we can pretty much guarantee, and this one we should be able to get pretty fast. We just did that in like no time at all. I don't really have a start time, but that felt pretty slow, or that felt pretty fast. So yeah. All right. Are there any more questions? How do I decide the original -1 charge? Okay, so I take a look at all of the amino acids here, right? So how many of these amino acids at fully basic pH have a negative charge, right? If you think about the ones that do, right? Aspartate is going to have that negative charge. Glutamate is going to have that negative charge. Cysteine is going to have that negative charge. And tyrosine is going to have that negative charge, right? We don't have any of those amino acids, right? So the only negative charge that's going to show up is going to be from the C-terminus that I didn't draw. So that is going to be the only source of negative charge. So that's going to be a -1 charge whenever everything else is deprotonated. So that's how I started from the -1 charge, and then I just added 1 because you're adding a proton each time you cross one of those pH or pKa lines. So that is how I found it out. All right, any more questions? All right, if there are no more questions, then good luck on y'all's test tomorrow. You're gonna do great. Just don't stress yourself out too much.